In the rapidly evolving landscape of generative AI, the pivotal role of vector databases has become increasingly apparent. The selection of a vector database for generative AI applications is contingent upon the particular needs and feature of the generated vectors. So in this video, we are going to be discussing the top 5 vector database options for generative AI applications. So the first one on the list is the FAIRS or the Facebook AI Similarity Search. FAIRS is an open source library by Facebook's AI research lab designed for efficient nearest neighbor search in high-dimensional vector spaces. It excels in tasks requiring quick similarity searches, making it valuable in generative AI applications. Let's quickly see an example of how you can actually use FAIRS to perform similarity search on the nearest neighbor. So in order to do that, you firstly need to import the libraries, and these are the two libraries that you need to import. And for the FAIRS, you can either import FAIRS for the CPU or for the GPU. After that, I am creating the sample data, and for that, firstly, I am creating a 64-dimensional database of 100,000 vectors and a query set of 10,000 vectors. The vectors are randomly generated and have a component that increases incrementally to make them ordered. After that, a face index object is created by specifying the dimension. This index is currently untrained, and after that, the vectors from the database are added to the index using the add method. And once this is done, the next thing that we are doing is we are printing the index training state and the total number of vectors which are generated. Now the next thing is to perform the similarity search. So here, a search is being performed to find the 4 nearest neighbors for the first 5 database vectors. This is a simple sanity check. The neighbor indices and the distances are returned as a result of this search function. And then we are also printing the indices and the distances. And then finally, we are performing the actual search in which we are finding the 4 nearest neighbors for all the 10,000 query vectors. And then the indices and the distances for the first 5 queries are printed. So now let's go ahead and see what is the output of this. So let's have a quick summary. I have created a 64-dimensional database having 100,000 vectors and a query set of 10,000 vectors. Out of these, I am performing the actual search where I am gonna find the 4 nearest neighbors of all the 10,000 query vectors. Here k is equal to 4 and xq is equal to 10,000. So we are gonna find the 4 nearest neighbors for all the 10,000 query vectors, and we are printing the indices and distances for the first 5 queries. Now let's quickly run it to see the output of the similarity search. Once you run the file, you will see that we will have 4 different matrices. Firstly, it is printing true, which is the state of the index that it is trained. After that, it is printing 100,000, which is actually the total number of database size. And after that, you can see that we have a total of 1, 2, 3, 4 different vectors because we want to see the 4 nearest neighbors, and we are printing the 5 distances. We are printing the distances and the indices of the first 5 queries. So here we have 5 rows in each matrix, which is actually representing the neighbors of the first 5 queries and the indices of the first 5 queries. In this way, you can use FAIRS to perform similarity search in order to find the nearest neighbor. On number 2, we have Milos. It is a vector database which is highly scalable, and it is built for scalable similarity search. This database can manage trillions of vector datasets and supports multiple vector search indices and built-in filtering. In order to use Milos, you have 2 options. Either you can use it on the cloud or you can install it locally. If you want to use it on the cloud, then you can go ahead and sign into Zillies, and it will provide you cloud services for using Milos. So firstly, you have to create a cluster, and once your cluster is created, then it will provide you the public endpoint and the token, and these are the 2 values that you can use in your local system as well in order to establish a connection with your cloud cluster. So I'm going to show you that too. Here in my VS Code, I've already written the code to establish the connection with the Milos on the Zillies. If you have to import PyMilos, that will include collection schemas, field schemas, and data type, etc. So in order to use Milos, firstly you have to establish a connection with your cluster. So here in the endpoint, you have to provide this path which is present right here, and for the token you have to paste the API key. Once you have pasted the two values, now the next thing is to firstly define the schema in order to create the collection. So in order to define the schema, I am creating 4 different fields. First one is the book ID, then we have the book name, word count, and book intro, and using the field schema, I am setting the value for all of these. Then I am setting the collection schema to include book IDs, book name, word count, and book intro as the fields. This is the description, and I have set the dynamic field to be true. Then the name of my collection is gonna be books. And once you have set the collection name, now you simply have to use the collection from the PyMilvis, in which you have to provide the collection name, which is book. Then for the schema, you have to define the schema which we have previously created, and the shards number are actually 2. Now let's go ahead and run this. And if the connection is successfully established, then it will create a new collection in our cluster running on Zealous. Okay, so it executed without any error. This means that the connection has been successfully established and we have created the collection inside our cluster. So let's head back to our cluster. Here is my cluster. If I go to the collection from right here, you will see that now we have a new collection by the name book. And once you have the collection, you can go ahead and move towards the playground, in which you will have the option to insert the data, search the data, query the data, and get data, upsert data. You have this text box in which you can insert the data in the form of JSON, and once you run it, it will send a post request to your cluster that contains your Milos collection, and the data will be inserted inside it. On number 3, we have ANOI, also known as Approximate Nearest Neighbors. Oh yeah, it is a C++ library with Python bindings, provides a flexible and efficient approach to approximate the nearest neighbor search. ANOI is designed to handle large datasets, providing quick and scalable methods for finding approximate similar items in high-dimensional spaces. Now let's quickly see how you can actually use ANOI. So you have to import these 3 libraries in order to use ANOI. So after importing the required libraries, the first thing that we need to do is to define a node class containing the left and the right subtrees. Here you can see that we are defining the left node, this is the right node, and these are the vectors for the leaf node, and it evaluates false if it is not a leaf. This code actually allows the queries to quickly traverse down several trees in the forest simultaneously to find the nearest neighbors. The forest allows exploring several branches at once to find the neighbors faster than a single tree. The balanced tree ensures no leaf is too much larger than the other. So you can see that right here, firstly it is creating the vectors for the left and the right node. After that, it is splitting the vectors in order to search for the nearest neighbor. Then here we are checking that the newly created tree using the left and the right is mostly balanced. And if it is imbalanced, then we are gonna redo the tree build. After that, we will look for in both the left half and the right half of the tree and will return the node if it matches. Then it will recurse on the left and the right half to build the tree again, and using those trees, it will build the forest. And then once the forest is created, then we are gonna query the forest in order to find the nearest node. On number 4, we have Pinecone. It is a vector database that is designed for machine learning applications. It is fast, scalable, and supports a variety of machine learning algorithms as well as generative AI applications. Here, we are gonna start by creating different vectors and inserting them inside our index. Since we are gonna use the test index again and again, so in order to refer it, firstly, I am going to create a client instance that targets the test index, and to do so, I am going to create a new variable index, inside which I am going to pass pinecone.index, and inside the index function, I am going to pass the name of my index, which is test index. So in this way, we have created a client instance that targets our index, and whenever we want to target this instance, we will simply refer to this index variable. Now let's actually insert the vectors inside the index, and for that I'm going to use the index.upsert function. So whenever you want to insert the data inside the index, you have to use the upsert function. Inside the upsert function, I am passing 2 things. First thing is a dictionary by the name vectors, and this dictionary has 2 key value pairs. The first one is for the ID of the vector, and the second one is the values, which is again a list of different values for the vector. So in this way, inside this index, at once I am inserting 4 different vectors by creating a dictionary of vectors having ID and values. And then the next parameter is the namespace. So as I've discussed earlier, that namespace let you partition vectors within a single index. So instead of having all the data inside a single index, one after the other, you can actually partition your data into different chunks on the basis of different namespaces. So I've created a new namespace by the name ns1. And similarly, I am going to again use the upsert function, inside which again I am going to pass a dictionary of vectors having ID and value. And this time all these vectors will go inside my namespace, which is ns2. So in simple words, I have partitioned my index into 2 namespaces, each containing 4 different vectors. So overall there are 8 vectors inside the index, which are partitioned into 2 different namespaces, right? Let's verify that if we have successfully created the vector and inserted it into the index or not. Let's run this project to verify it. Alright, so the process finished with exit code 0. This means that all of these codes have run successfully. Now in order to verify it, let's head back to our Pinecone dashboard. Let's refresh the page, and now you can see that the vector count is 8. This means that 8 new vectors have been successfully added inside our index. So in order to fetch the vectors inside our index, we can use the index.fetch method, and inside it you have to pass the IDs of the vectors whose value you want to print on the IDE. So let's say I want to print out the vectors whose ID is vec1 and vec2. So I can write it in the form of list like this. So inside the list, so firstly you have to pass the ID of the first vector and then the ID of the second vector separated by comma and so on. And I'm going to pass all of this inside the print function so that I can print the values which are returned by the index.fetch function. Now I'm gonna go ahead and run the project. Okay, so it has given me nothing in place of namespace and the vectors. This is because I haven't provided the namespace name. So outside the square bracket, here I'm gonna paste the namespace name, which is ns1. So now I want it to fetch the vectors having ID vec1 and vec2 from the namespace ns1. Now let's go ahead and run this to see how it responds. Okay, so now it has fetched the correct data. The namespace is ns1, and for the vectors having ID vec1, these are all the values. And for the vector having ID vec2, these are all the values which are present inside the vector. So in this way, you can fetch any number of vectors you want. You simply have to pass the namespace name with the vectors if you have multiple namespaces inside the index. And then finally, on number 5, we have hierarchical navigable small world. It is an algorithm for approximate nearest neighbor search. It constructs a hierarchical graph structure allowing for efficient and scalable searches in high-dimensional spaces. It is commonly used in vector databases and applications where quick and approximate similarity searches are crucial. Now let's quickly see how you can perform the nearest neighbor search using NHSWLib or the Hierarchical Navigable Small World Library. So here is the code in order to perform the nearest neighbor search. Firstly, I am importing the NHSW library and NumPy. Here the NumPy is being used to generate some random sample data points to the index. The data here is actually a 2D array with 1000 rows, also known as the data points, and 128 columns, which are also known as the dimension. Next, a HNSW index is created for the 128 dimensional vector space using the L2 distance metric. The index is initialized to hold 1000 elements with some specific parameters that control the trade-off between the index build time and the search accuracy. The simple data is then added to the index using the index.addItems function, so that each row becomes an index data point. After that, a new random query point is generated. Then we are using the index.knn_query method, which finds the 5 nearest neighbors to this query out of the index data points. It then returns us the labels, which is actually the row number, as well as the L2 distances to each neighbor. And then we are simply printing the label, which is the row number of the nearest neighbor as well as the distance. So overall, this code takes a set of vector data, builds an HNSW index from it, then uses the index to quickly find the nearest neighbor for the generated query points and displays the row number, which is the label, and the L2 distances between the neighbors. Now, if I go ahead and run this, it should provide me the distance and the neighbors. Okay, so it is giving me an error because of this library. So I'm gonna use an extension here, which is the code. So if I ask it, what is the output of this code? So it will provide me that the output of this code are the labels, which is actually an array containing the integer labels, the row numbers in the data array of the 5 nearest neighbors to the query point. And then the second thing is the distances, which is actually an array containing the L2 distances from the query point to each of its 5 nearest neighbors. So overall, the output will be like nearest neighbors. Firstly, it will provide us the labels. So these are the 5 rows, which are the 5 nearest neighbors. And then in the distances, we are actually providing the L2 distances of each of the row. So in this way, you can perform the nearest neighbor search using an HNSW library. I hope you enjoyed exploring these incredible vector databases as much as I did. Thank you.